Hi students, welcome to my lectures. Okay, in short, what we are discussing at the present moment is diagnostic and troubleshooting in a non-ideal reactors. Okay, that means through the tracer curve experiments, can we able to identify what kind of non-ideality existing in the reactors? For example, let us take the case of PFR plug flow reactor, and uh, is it behaving ideally or non-ideally? Simple, put a tracer and at the exit and measure the tracer based on the information about the RTD, that means residence time distribution curve for the tracer. We can able to identify the non-ideality in the reactor. Okay, so let us assume that there is a PFR. Okay, and we have injected some amount of tracer. Based on this information, can we able to identify? Presently assume that this particular reactor is having the bypassing non-ideality. If it is, what is the bypass? That means there are certain molecules which follow the shortest route and exit the reactor. There are molecules which actually gone through the reaction through the entire volume which participate in the reaction. That means the short-lived element, that means which spends a very least amount of time, does not mainly contribute to the conversion. So if that is the case, can we able to identify this particular non-ideality through the tracer curve experiment? Simply inject a tracer and detect the tracer at the exit. Then compare the ideal CSTR curves with the non-ideal CSTR curve, so you can able to get an idea. For example, assume that this particular graph behaves ideally. Generally ideal CSTR, that is very, because we have to represent with a straight line, but here we have represent with a slight curve because for the simplicity of understanding this particular curve, instead of the straight line I have represented this E of t curve for a ideal CSTR. That means this particular ideal CSTR, it's a kind of a very narrow curve. Okay, that means whatever the tracer you have injected, majority of the tracer comes at only around very close time. So this is called a near ideal plug flow reactor. So that we use this curve and compare with this non-ideal curve so that we can able to identify the bypassing issue in the particular non-ideal reactor. Okay, so what is the near ideal plug flow reactor? Simple. The space time of the reactor is nothing but volume by volumetric flow rate. That means the injected tracer will come at a particular time which is called, after certain point, after traveling through the reactor, it come at the exit. That exit point is nothing but the after time tau, which is called the space time of the reactor. This is how the ideal near ideal residence time distribution graph should look like. How the f of t graph should look like? F of t, that means after time tau spending in the reactor, all molecules, that means entire all the fraction, that means 100% of the molecules come at the time which is tau, which is represented by f of t curve. Now let us compare these things with the non-ideal E of t, that is residence time analysis and distribution curves. There is if there is a bypassing issue is there in the reactor, what happens? There are certain amount of tracer molecules which exit the reactor at the early, and there are molecules, remaining molecules exit, that is most of the molecules will travel through the reactor which contribute to the conversion, comes at the late. That means you should see the two peaks. One is which early peak which contributed to the bypassing of the molecules, and second peak which is main peak contribute to the reaction and conversion in the reactor. That means you are identifying more than one peak. That means indirectly there is a bypassing issue is there in the particular reactor. So if the reactor is behaving ideally, there should be only one peak, because most of the molecules spend almost the same amount of time. You should get this kind of sharp and narrow curves, and instead you are going to see two curves. One is a short, early curve, and one is a late curve. Early curve is indicating the bypassing molecules, late curve is indicating the remaining molecules which contributed to the reaction in this particular reactor. Okay, that is why you can able to see this, how the f of t graph looks like. Okay, The what is the space time of the actual molecules that is going to the reactor, which is nothing but, I mean, you can able to devise a strategy like this. Total volumetric flow rate has been divided into two cases. One, before entering the reactor, it will directly exit the reactor. If that means it is representing the situation here. That means there are molecules which go faster through the reactor and does not contribute. If it is does not contribute, simply you are represent this such situation in the schematics. That means divide the volumetric flow rate into two. One is bypassing volumetric flow rate, which is VB, and actual volumetric flow rate V. So the total volumetric flow rate is a contribution from the two, which is volumetric flow rate which is bypassing plus volumetric flow rate that is gone through the reactor. Then what is the space time of the reactor? Actual reactor is nothing but tau into BR. The reactor is which is having the bypassing problem. The space time of such a reactor is represented by the tau BR, which is the total volume of the reactor, that is, and divided by volumetric flow rate that is entering through the reactor, which contributed to the conversion. Okay, this is how the space time of the reactor, and compared to the actual, that means you can see the space time of the ideal reactor is V by nu 0, and space time of the bypassing reactor is V by nu BR, because nu BR is less or higher. This is lower than nu 0. That is, nu BR is lower than nu 0. That means tau BR will be higher than tau. That is, space time for the bypassing reactor will be higher than the space time compared to the ideal reactor. Okay. Then how the f of t graphs looks like. Okay. Depending upon how much amount that is bypassing. How you can able to say that how much amount of volumetric flow rate got bypassed. Simple. Fraction bypassed is nothing but volumetric flow rate that is bypassed divided by total volumetric flow rate, which is called fraction bypassed. What is fraction passing through the reactor? That is 1 minus VB by, that is total equal to 1. If this much fraction is gone into bypass, the remaining fraction 1 minus nu B by nu 0 gone into the reactor. So how the f of t graph looks like. Let us see how the ideal CSTR graph looks like. That and at time t equal to tau, all molecules exit the reactor. Now, because of the bypassing, the f of t graph will not start at a 0 point at t equal to tau. F of t starts at initially because few amount of molecules already bypassed at time t equal to 0. That means the graph starts at very early time t equal to 0. Then the remaining molecules come at tau BR. The initial molecules come at time t equal to 0, which is this point. The remaining molecules come at tau BR, which is the space time of the reactor. So you can see this step once. Okay, if you see this step kind of input in the kind of cumulative distribution graph, then you can able to indirectly identify that there is a kind of bypassing problem is in this particular reactor. Okay, let us do a small example. Find the space time of the plug flow reactor which is having the issue of bypassing or channeling. So bypassing, people use the word bypassing and channelers, so both are same almost. Find the space time of the plug flow reactor which is having the issue of bypassing or channeling. It is given 20% is getting bypassed. So let us find out the space time of this particular reactor. The total volumetric flow rate going into the reactor is 1 liter per minute. Total volume of the reactor is 5 liters. And nu B is the volumetric flow rate that is getting bypassed in the reactor. Nu BR is the volumetric flow rate that is gone through the reactor, that is which is contributed to the reactions. And let us find out, it is given 20% is bypass, that is bypass volumetric flow rate divided by total volumetric flow rate is 0.2. Therefore nu B is equal to 0.2 into nu 0. Therefore nu BR is nothing but total volumetric flow rate minus volumetric flow rate in the bypass stream. So 1 minus 0.2 into 1 is 0.8. Okay, then what is the space time of this particular non-ideal PFR, which is volume by volumetric flow rate, which is nu BR. 5 by 0.8, 6.25 minutes. Okay, what is the, if this reactor would behave ideally, what is the space time of this particular reactor? Nothing but space time tau equal to volume by volumetric flow rate, which is 5 by 1 equal to 5 minutes. Now you compare. If the reactor would have been behaved ideally, the space time of this particular reactor is 5 minutes. Because this reactor is behaving non-ideally, the space time because of this particular bypassing is 6.25 minutes. Okay, that means because of the bypassing issue, the effective space time in the reactor has got increased. That means molecule effectively spend more time in the reactor because of this particular bypassing issue. Hope you have understood what exactly the PFR, how the tracer curve experiments helps us in identifying this particular non-ideality. How people will identify? It's very simple, that 20% bypassing. How I can able to get it? Through the curves. Okay, through the f of t curves, e of t curves, I can able to find out vb by nu b by nu 0. That somehow I this cumulative distribution graph indicates that particular percentage of bypassing in the reactor. Let us meet with the new lecture.